Hi, everyone. Well, now we're going to begin the last topic for our class, superconductivity, the ability of some materials under some conditions to conduct electricity with zero resistance. This is a fascinating subject. There are obvious applications, and it's interesting because it's an example of a macroscopic quantum phenomena. In a superconductor, a macroscopic number of conduction electrons somehow manage to act like a single quantum object. Well, we're going to have to rush through this topic a little bit. Today, we're going to introduce the discovery of superconductors, a little bit of their history, and talk about their basic properties, okay? And next time, I'll try to give you an idea of the underlying theory which leads to superconductivity. Okay, well, I think we'll get started. So let me start by showing you an outline, and then we'll go on from there. 1 second. Okay, here, let's look at an outline. So I'd like to start by talking about the discovery of superconductivity and its history, but then I want to talk about some of its basic properties. Of course, superconductors exhibit zero resistance. In the superconducting state. That's their most famous property, I guess. But a second one that's equally important and just about as weird is called the Meissner effect. Superconductors expel magnetic flux when they cool below the transition temperature. Another interesting feature, critical feature, superconductors possess an energy gap, which separates the superconducting states from the normal conducting states. And this energy gap is an essential part of why they behave as superconductors. And it's quite different in a way than the energy gap that we see in semiconductors. Okay, so we'll have to take a look at that. Finally, we'll see that superconductors all possess a critical magnetic field. Above which superconductivity is destroyed and the material becomes a normal conductor. And there are actually two types of superconducting materials, depending on their properties and magnetic fields. Very imaginatively, these are called type 1 and type 2. We'll learn that type 1 materials are simpler in a way, but in type 1 materials, superconductivity is destroyed at very small magnetic fields, which makes them kind of useless for applications. In type 2 superconductors, though, superconductivity can persist up to very large magnetic fields. And so these are the basis of applications like superconducting magnets and other devices. Well, that's what we'd like to talk about. Let's start by talking about the discovery of superconductors. Hold on for a second. All right. Well, superconductivity was discovered quite some time ago in 1911. And it was discovered by this fellow, H. Kamerlingh-Onnes, here pictured with van der Waals in front of his apparatus. Kamerlingh-Onnes is famous because he's the first person to liquefy helium. Helium liquefies at 4.2 Kelvin, okay, close to absolute zero. So he's the first person to work out how to refrigerate gases to the point where you could even liquefy helium. And of course, once he could do this, he could do all kinds of low temperature experiments and study the properties of materials at low temperature. And in 1911, he found that mercury, when cooled close to absolute zero, went through a transition. At 4.2 Kelvin, the resistance of a sample of mercury would drop to zero, to as close to zero as could be measured with his equipment. Okay? It's kind of it's of course an amazing and very interesting phenomenon. But that's the discovery of superconductivity. Excuse me. Here's a brief history from that point. So superconductivity was discovered in 1911, and this is a great mystery that stood for almost 40 years before it was really addressed. In 1933, Walter Meissner discovered the Meissner effect, that superconductors aren't just perfect conductors. They also exhibit this phenomenon where they expel a magnetic field when they're cooled below the transition temperature, something we'll talk about a little bit later. In 1935, a first theory of superconductivity called the London theory was developed. This is a phenomenological theory which explains the Meissner effect. That's its real contribution. Much more interesting theory, really, in 1950 is the Ginzburg-Landau theory. This posited a superconducting wave function, that the electrons in a superconductor were somehow described by a single wave function. And based on that, it could explain much of the phenomena that are observed in superconductors. Finally, in 1957, John Bardeen, Leon Cooper, and Schiefer developed the BCS theory. In the BCS theory, the conduction electrons in a superconductor form a superfluid condensate of electron pairs. And it's this superfluid condensate which can flow without resistance. And they posited a mechanism for the formation of pairs, which we'll talk about in our next class. But it's due to the electron-phonon interaction. So this is the first kind of complete theory of superconductivity, which could make detailed predictions that could be compared with experiment. And it's really the basis of modern theories of superconductivity as well. Well, that was 1957, so you might say in 1957 this was kind of a solved problem, and the field went into decline for a while until some kind of revolutionary discoveries later in the century. So if this is the early history of superconductors, the modern history begins in 1986, when Bednorov and Mueller discovered superconductivity in lanthanum-based cuprates and observed a startlingly high transition temperature for this material. Very soon after that, Chu Qingwu discovered superconductivity in yttrium barium copper oxide, another cuprate material. Only here the transition temperature was much higher, 97 degrees Kelvin, which is really transformational. This set off a wave of important work on superconductors, which continues to this day. In fact, these materials are still not that well understood, even now, so many years later. By the way, 1986, that was the first year that I was in graduate school. And YBCO was developed in 1987. Two big things then. The supernova 1987A, so the first supernova in our galaxy in quite some time, and then the discovery of high temperature superconductors. Anyway, in 2008, people discovered a new class of superconductors based on iron, composite materials containing iron, which is really, really weird, because we'll see that one of the things about superconductors is that they can't be magnetic, but these materials are magnetic. So that's really startling. And some of these exhibit very high transition temperatures as well. And finally, very currently, essentially right now, people have discovered superconductivity in superhydrides, in very hydrogen-rich materials at very, very high pressures. This phenomena was predicted before, but earlier, but only experimentally investigated now in the last just the last couple of years. In particular, in October of last year, a paper published in Nature showed room temperature superconductivity in a carbon sulfur hydride at 267 gigapascals, but at room temperature. It's a really fascinating discovery. Here, I wanted to just show you now a table of showing the transition temperatures of all the important compounds that people have discovered, starting with mercury back in 1911. Okay. So first there's a class of materials here, mercury and then lead, and then all of these niobium-based materials here. So niobium-based alloys, and a few other materials, and finally magnesium diboride fairly recently. All of these materials are kind of traditional superconductors that can be explained by BCS theory. Here, I'll shade them for you, okay? So you've seen a current development that's gone on over the years, leading to materials with transition temperatures as high as 35 or 40 Kelvin. In in 1986, the lanthanum cuprates and then YBCO were discovered, and other cuprate materials have been discovered since with very high transition temperatures. In fact, these are called high TC materials. And the high TC materials, some of these have transition temperatures as high as 170 Kelvin, okay? And there have been some evidence in some materials of phases with even higher transition temperatures, but it's not really, but that part is not really convincingly demonstrated. I mentioned the iron-based materials. So the iron-based materials were discovered in around 2000, and this shows their development as well. And finally, very recently, people have discovered superconductivity in superhydrates. So materials containing a lot of hydrogen, but at very, very high pressures. And fascinatingly, people have seen superconductivity now at temperatures up to basically room temperature in these materials. And at the last March meeting of the American Physical Society, there was a talk showing superconductivity well above room temperature in these hydrate materials. But that's exciting, but it's also, we have to be a little bit careful. First, let me describe how these materials work. So they're hydrates. So hydrogen is absorbed into material at very, very high pressures to get very, very high concentrations of hydrogen in the material. In essence, there was a prediction some time ago that metallic hydrogen, which only exists at very, very high pressures, could be an excellent superconductor. And in these materials, people are trying to use chemistry to force hydrogen atoms together in high concentrations without such staggeringly high pressures. Although the pressures are still quite high. Here's some data showing superconductivity at 262 Kelvin at 182 gigapascals. That's about 2 million atmospheres of pressure, okay? Pressures like these can only be obtained in devices called diamond anvil cells. In the diamond anvil cell, two diamonds that have flat faces are pressed together, and the material that you want to squeeze is pressed in between them, okay? There's a metal gasket material, and then the material you're compressing is in between them in some kind of pressure medium. We use diamonds because only diamonds are strong enough to exert this kind of pressure. On the other hand, the area that we're compressing is rather small. So we actually don't need a tremendous amount of force to squeeze these together hard enough to reach those pressures. We just need to have materials that are strong enough so that they won't break under those conditions. Okay, I got to do some work with diamond anvil cells back when I was in graduate school, but nothing quite like this. Okay, well, that's a quick look at the history and some current work in superconductivity. I think we'll stop here and then continue with our tour on the next video. 1 second.